All right, so remember at the first lecture we had, we talked about difference between law and theory, right? Are we okay with saying this theory is good? I don't know. Let's see what it is, and then we'll see, right? So we can't really see these little particles of an atom, but we say they are the way that they are because of physics, because of all of the other things that we know. All of the other laws tell us, okay, it's got to be like this. Now, we started this theory like, 3,000-4,000 years ago. This Greek philosopher, these are the old guys, right? These are the old smart guys. And he just says, okay, an atom is just a small, indivisible particle that everything's made up of. And that's all he said. He was a thinker, and so he says, it's got to be made of particles. Okay. But we didn't have any tests. It wasn't any scientific process that backed it up. So it was just somebody's thought. And just like Aristotle, you heard of Aristotle? Well, he says, this is how it is. And 1993, they forgave Galileo. Somebody forgave Galileo because he went against Aristotle. Okay? Don't hold on to your beliefs is what I'm saying. I mean, unless they're right, and there's no way to know until we test it out. And I'm not saying your religious beliefs are, I'm just saying about science, right? Okay. So that's what happened a long time ago. We have these little indivisible particles called atoms. That's what everything's made up of. And then a long time later, like probably 2,000 or more years later, I don't remember the dates, I'm not a history buff, but like, let's see, it's probably more like 2,500 years after, okay? So John Dalton, he was actual scientist, and he come up with an actual atomic theory that was based off of science, okay? And so let's talk about his points, and it was just, basically, he just changed a few little things, right? We're not going to talk about exactly how he did this, but okay. He was still before the time of the scientific process, and so he didn't even, it was more of a, okay, we'll take what Democritus says and we're going to put it in a format, here we go, science format, and okay, this is what it is, okay? And so he says, and it was pretty close for the most part. There's a few little flaws and stuff with this theory. So I'm only going to tell you the parts that are still golden, okay? So the atomic theory today states that all matter is composed of atoms. And what are atoms? Maybe you should put this definition in there. The smallest particle of an element that retains the element's identity. And you guys are okay with what an element is, right? The things on the periodic table, okay? The substances on the periodic table. Smallest particle of an element that retains its properties. So all matter is composed of atoms. The air we breathe, to the metals that we wear on our hands, okay? All composed of atoms. Second thing, part of the atomic theory is atoms of a given element are different than atoms of another element. Atoms of a given element are different than atoms of another element. So if we're talking about a gold atom, all gold atoms are the same. Now, we'll find that that's a little bit off. Okay? But basically, they're the same. There are parts of them that are the same. Okay? But atoms from different elements, they are different. They're completely different. And we'll talk about that. Okay? Next part is compounds. You guys understand what compounds are? We'll give a definition after this. Compounds are a combination of atoms So I'm going to put in parentheses here. It's a small whole number ratio of atoms that make up the compound. Any questions on what that's saying? Maybe we'll give examples, okay? So compounds, what's a compound? It's a combination of two or more elements, chemically combined, right? So two or more elements chemically combined.
Like a sodium chloride?
That's it. Combined. So yeah, let's do some examples here. Like sodium chloride. What's sodium chloride, Aiden? This is table salt. We eat it every day, right? What else do we put in our body every day that we have to live off of? Water. And we breathe oxygen, right? Well, that's not really a compound, is it? That's just a single element, okay? Are we good? So small whole number ratio. The ratio of water is ratio 2 to 1, right? 2 hydrogen atoms to 1 oxygen atom. You get that? We don't write a 1. It's kind of like in math we write x. We don't have to write 1x. You with me? We just negate it. Just don't write it. But if there's no number, it means there's a 1. And we put it after the element. So there's 2 right after the hydrogen. That's 2 hydrogens. There's not a number after the oxygen, so that's 1 oxygen. Question?
Yeah, so on the exam, if you ask us what a compound is, which definition would be correct?
Right here. So this is not a definition. That is step 3 to the atomic theory. Not step 3, but point 3. So this yellow one in yellow, that's the definition to a compound.
Thank you.
Thank you. Are we good? And we can do table sugar, C12, do a different color, I guess. C12H22O11. Do you have to memorize these things? No, you don't. It's just another example. Stuff we breathe out, carbon dioxide, CO2. We can go on and on and on. A lot of different substances that are compounds, okay? And did we talk about pure substances in here? So that's just an example of a pure substance, right? Okay. And 4 is atoms cannot be created or destroyed. Or, let's see. Yeah, that's good. Atoms cannot be created or destroyed. So what does that tell us? Atoms are ageless. If, well, as old as the universe anyway, right? But are they older than that? If we believe in the Big Bang Theory, which I don't know why. I mean, the only reason we wouldn't is because we don't know what it states, right? Or maybe we have religious beliefs that maybe we feel like, anyway, that's not the topic. So, the Big Bang Theory states that all of the matter in the universe was close. Whether it was or wasn't, who knows, right? No idea. No one does. So that's the part that we don't know. But anyway, so everything's close together. Everything as we know it. And then, now everything as we know it is out here. But it's still there. What was it before the Big Bang? Still atoms. As far as we can tell, right? Doesn't make sense for it to be anything different. It's still matter. Does that make sense? Okay. This is always true, no matter what, as far as we know, right? But part of the theory states that, in fact, Democritus and John Dalton, and they says you can't divide them. Okay? We can divide them, but not chemically. So how else? We'll talk about at the end of the semester. Nuclear chemistry. Pretty cool stuff. Okay? Are we good with this base atomic theory here? All right, so let's... Let's give a little bit of the periodic table. Now let's just keep going. Let's just keep going. No, we got to. All right. So if you look at the periodic, do you guys have a periodic table yet? Okay. You can download one or print it off. On the exam, I will print it off for you. Actually, I should have made some copies of a periodic table today. I didn't. So we'll see how far we get. Okay. All right, so on the periodic table, you guys ever seen one of these? Yeah? Okay, so you have different elements. If you look at the elements, for example, we have gold, which is AU. Silver, I'm just going to give a few, which is AG. Sodium, which is Na. Oxygen, which is O. What do all of these have in common? They all start with a capital letter. All elements begin with capital letters. The symbol does, right? Symbol begins with a capital letter. If it has a second letter in it, it's always lowercase. That's how we write it. Why? That's how it got set up a long, long, long time ago, and no one's changed it. That way we're all on the same page no matter what country we're in. Yeah? So become familiar with these. Start right now and become familiar with them. I'm not saying you have to. Don't memorize the numbers. That's going to be icky. I mean, there's a 3-year-old girl on Ellen DeGeneres show. You ever see that little video?
Yeah.
She memorized them all and she knew it all. You guys don't have to do that. But just know where they are on the periodic table. And if you familiarize yourself with them, then we get to an exam, go right to, okay, there it is. What's the information on it? Okay, I can use it. Okay? All right. Let's start talking about what an atom is made of. Any questions so far? So subatomic particles. So after John Dalton, then a physicist, not a chemist, a physicist discovered that atoms probably have a negative charge in them. You guys ever heard of a cathode ray tube? I bet you've seen one. They're old TVs, the tube TVs. Those are cathode ray tubes, okay? But the ones that they use in science, the ones that J.J. Thomson used look something like, and forgive my art here, something like this, and it had a little stand on it, and you'd have a ray here. So this is a glass tube. This is an awful drawing. A glass tube, nothing was in it except for a gas, okay? And put electricity through it, so this is maybe the positive end, negative end. Put electricity through it, and you saw this beam of light. Cool, right? And this physicist, he was playing with this quite a bit. And he says, I like magnets. Let's put a magnet up to it. And what happened is it deflected. He turned the magnet around, it went this way. Okay, so it repels or attracts depending on if it's north-south pole. And charged objects do this. So we rub our balloon on our head, right? And we can notice what happens to the charge when you put a magnetic field by it. So there must be a negative charge in there because it's acting like a negative charged particle, according to how we describe negative, right? Whether it's negative or positive, okay, that's just depends on the person who named him that, right? But we're not going into that, okay? So he discovered there's negative charged particles. So he says, okay, here's the atom with a bunch of negatives in it. Still a small particle you can't break and has the same properties that John Dalton said, but okay, it has negative particles in it. And then another scientist named Ernest Rutherford, he did a test that was pretty cool, an actual test. So we got this alpha particle launcher. An alpha particle is a helium nucleus with a positive 2 charge. So it's shooting this alpha particle out. He says, okay, let's see if we can shoot this at atoms and see how it behaves. Because we can't see it, so let's see what happens. So we got this gold foil. Why gold? Because gold doesn't react very well. Just stays wonderful. Why foil? He wanted it as thin as we can get it. Because if you have a big, thick thing, yeah, it's going to just bounce off like everything else does, right? So he wants it real thin. Let's see what happens. So just to make sure everything was measured right, he put this photographic, I don't know exactly what it was, some sensitive film that would detect these alpha particles. You shoot it at it and it would detect it. You might have to do some, kind of like, anybody ever take the old photography classes where you have to actually develop your own pictures? Okay, so it's something kind of like that, right? So he put this through here and shot this in, and this is the pattern that he got. Most of them went through and smacked our film. And I'm sure it looked more sophisticated than this, okay? But most of them went through, but some of them didn't go through. So that told them two things. That an atom is mostly empty space. Stuff goes right through it, okay? And it also says they're all deflected. None of them went straight through. They're all deflected. That means the center of the atom must be positively charged, because positive charges repel. Yeah? That makes sense? How we know something is, even without seeing it. Okay. And you could even repeat this, and it's been repeated, and you could find out this is what happens. Okay? They even have little discs of alpha particles, and you can shoot them. You don't shoot them, you just let them shoot by themselves because they're going. Okay? When we talk about nuclear decay, it just happens without you doing anything. Okay? Anyway, that's not the topic. So we found that those two things. And then his student, Niels Bohr, found that, okay, that's good. We know that. But electrons, he discovered that electrons only can carry a specific amount of energy. So he came up with this model of the atom. In fact, Ernest Rutherford's model looked like this. You ever see that? Okay, where the electrons go around. Okay? You didn't know how they went around, but they're just on the outside, mostly empty space. And the center is positive. And then Niels Bohr, notice I'm not writing these names down. I'm not going to test you on these names. But I'm just trying to help you to understand how we know what we know. Okay? Actually did tests on this. And Niels Bohr, he measured how much energy these electrons had. And you can get these electrons to jump out. They jump out and then they come back, and you can measure how much energy based off of the light they emit when they do this. So that's all I'm going to say about that. We're not going to get more into that. So he measured the energy. It says they have specific energy levels. So here's the positively charged nucleus. And here we have electrons on this one. And we have another energy level, a little bit out, looks like this, right? Well, that's what he said. And he's right on that they have a specific amount of energy level. He tested that. But the thing that was wrong with his model is he was thinking potential energy. You guys understand potential energy? It's energy related to position, right? So this pen has potential energy. If I let go, it turns into what? Kinetic energy, energy of motion. I'm not going to, just giving you a little background, okay? And so Niels Bohr was thinking, okay, they have the same amount of potential energy. So he used the planetary model. They're at fixed distances around the nucleus. And that's just how it is. And you have an atom with more electrons, then it has just more energy levels, right? And then within 100 years ago, we come up with the quantum mechanical model. And that's what it is today. That was within 100 years ago. Are we going to get any further? Is that just it? My guess is there's more to learn, right? More to learn and more to change. This theory's been changing over the last thousands of years. So possibly it's going to change again. It didn't get discarded because all of these things that I mentioned have been clarified and tested again, and not just by one person, but several scientists in different countries, and just to make sure it's just they follow the scientific process, and this is how we know. Are we good? The quantum mechanical model. You want to know about that? All right. I can't draw this, so I'm going to give you an analogy. I still can't draw it. What does that look like? A fan blade, right? Okay, that's what it is. See? I could be an art major now. Okay, we got a fan blade, and we can see where these fan blades are. There's one right there, there's one right there, there's one right there, yeah? And now let's turn it on. Turn the fan on. What's it going to look like? A bunch of blur, right? So where's the fan blade? Somewhere in that region of space. You with me? And that's what we know about electrons. They're somewhere in that region of space. They're not right here, somewhere around here. They're in a 3D space moving around somewhere. Yeah? Sometimes they could be right there. Sometimes they could be right there. How? If they're right here, they must be moving faster. But the amount of energy stays the same. So Neil Bohr nailed it. Okay, and this guy was, what's his name? I don't remember. Gosh. Erwin Schrödinger. Okay, that's the guy. But again, you don't have to know. I'm not going to say, and so what did Erwin Schrödinger say? On what date? No, I'm not going to do that, okay? But does that kind of make sense? But how do we know this? We got new technology, electron microscopes. We can't see an electron, but we can see their behaviors. You with me? And so maybe it's going to change, and we'll get into that a little bit in just a little bit, okay? Well, let's see. Yeah. I don't think we need to worry about that because we're not going to test you on the electron configuration, which deals with all the quantum mechanical model. We'll just say, okay, that's how it is. Good? All right, so let's talk about the subatomic particles. So let's make a table. So we got the particle. We got the symbol. We got the mass. We got, and we'll call this relative mass. You guys know what relative means? In comparison with something else, right? Okay. So we're not going to talk about the mass of an electron, proton, neutron, because they're just tiny, times 10 to the negative 24 kilograms, right? Tiny, 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 and that's icky yucky. So we're, in fact, and we're not just doing that because I'm trying to keep things simple. We're doing that because that's what everybody does. That's what it's on the periodic table that way, okay? And we'll talk about relative charge. Same reason. And let's talk about location. And most important thing are attributes. Okay. Did I give you enough room to write it on your paper? I should have. Anyway. And you can take as long as you need. You can go down as far as you want, right? Okay, let's start with protons. Proton, and I'm not going to go through how we discover all these things. We're just going to move on, yeah? If you want to read about it, you can look it up. Okay? So the symbol for a proton is lowercase p with a positive exponent type deal. It's not an exponent. This is just a symbol, okay? Showing that protons has a relative charge of positive, but let's keep it simple. The actual number, remember when we started dealing with, we talked about scientific notation here, right? Yeah. So the number 0.0000018 zeros 1609, that's the charge of an electron, but it's also the charge of a proton. But they just have opposite charges. So we'll just say relative charge of a proton is +1, just to keep it simple. And not just simple, but it's even usable this way. Okay, so when we look at it and deal with it the rest of the semester, we're going to be dealing with these numbers. So make sure you get this down. Okay? Relative mass, the mass, like I said, is times 10 to the 24 something. Negative 24, rather. Not 24. And we're going to just say, okay, the mass of a proton, what's an easy number? 1, right? Mass of a proton is a 1. And where's it located? Anybody know? In the nucleus. This is what makes the nucleus positively charged. And the attribute is it determines the element. The number of protons determines what element we're dealing with. So, for example, if you look, I'm going to pull up a periodic table because I didn't print one out for you. Y'all have this? Can I move up? Okay. So here's the periodic table, and let's see. So hydrogen is number 1. So that means it has how many protons? 1. Helium has 2. Uranium has 92. That tells us what element it is. Does that make sense? Okay. And before we come up with this periodic table, we tried to organize them in a different way, and there were still problems, and it took a while to get to where it is today. And where it is today, this can help us to find new elements, and we found one in the last 5 years. I can't remember when. Okay? But anyway, so that's what protons are. Any questions with protons? Okay. Next one are neutrons. Neutrons. Neutron, lowercase n. What's the charge of a neutron?
Negative.
Good guess. Neutrons are called neutrons because they're neutral.
I was thinking
No, no.
electrons.
No, you're good. You're good. No worries. And so the mass, so the relative charge is 0. The mass of a neutron is basically the same as the mass of a proton. And these numbers aren't perfect, guys, but good enough to help us to make predictions. Yeah? So we're going to use these. When we look at the periodic table, this is what we use. And where are they located? Also in the nucleus. Now let's think about why. We'll talk a little bit more at the end of the semester, last chapter. But protons are all positive, right? If they're in the nucleus, how do they stay together? They should repel, right? Because they're the same charge. Like charges repel, opposite charges attract, yeah? How do they hold together? With the neutrons. As we get heavier and heavier and heavier, let's look at this. Here, this is like the mass, right? And this is an average, so that's why it's not a whole number, okay? But there's 0 neutrons in most protons. That's why the mass is 1. How many neutrons are there in most helium atoms? There's 2 protons, and the mass is 4, and they all have a mass of 1, have to have 2 neutrons. You with me? So it's same. You get here to calcium, it's 20, right? 20 protons, 20 neutrons. Are you with me? Do you understand what I'm saying? If you don't, say something right now. Okay? We'll get there. We'll do a little bit more. But as you get heavier, what about this? This is one of the heavier ones, uranium. 92 protons, how many neutrons? We did 40 minus 20 is 20, right? 238 minus 92 is?
146.
146. Whoa. A lot more a lot more neutrons. Why does it need more? Because there's more protons that need to be held together. So neutrons act like nuclear glue. Okay, that's a side note. Okay, to help us to know what neutrons do and what their purpose is. Okay. So what are the attributes? They determine the mass I thought protons also determine mass. But if we're talking about a carbon atom, it has 6. And the mass might change. What changes it? Neutrons change it. Okay? And that also determines the isotope. So maybe we should give you a definition of isotope. Isotope is an atom with the same number of protons, but a different number of neutrons. So it's the same element, but it has a different mass. And we'll talk about that a little bit later so that we can finish our table, yeah? Because you guys are like, oh, I quit it. How far do I go? Sorry. Are we good? So an isotope are atoms with the same number of protons, so it's the same element, but it has a different number of neutrons. Therefore, it has a different mass. Are we good? Okay, last particle we're going to talk about. If you want to learn more about particles, different particles than these, then you take nuclear particle physics. It's a pretty cool class, but you probably don't want to, right? All right. So let's go with electrons. Electrons, lowercase e, same pattern here with a negative exponent, because it has a charge of -1. The same charge of proton, just negative, right? And what's the mass? Basically 0. If you want to know the actual amount, it's like 1 over 1840 or 1 over 2,000, 2,000th. But if you do 1 divided by 1840 in your calculator, what does it give us? 0.0005. So basically 0. And we don't keep track of the mass of the electrons. We just cut it off. Good? When I say we, I mean chemists, actual chemists. Okay? Location, outside the nucleus. And what do they determine?
The chemical bonds, like chemical.
Yes. That means it determines the properties. And that in turn, that's what it would do. Perfect. So it determines the properties. Properties of the element and the charge. Well, hold on a second. Protons also have a charge, so why do electrons determine the charge and not the protons? You guys have a rubber balloon on your head? Stick it on the wall? How does it stick on the wall? Because opposites attract. When you rub the balloon on your head, what are you doing? You're either adding electrons onto the balloon or ripping them off, one of them. We can do some tests to figure out which it is, but that's not our purpose here. Okay? So the electrons change. Why? And why, this is a good question, why do electrons determine the properties, physical and chemical properties? Yeah.
Is it because they have a negative charge?
They do have a negative charge, but why would that determine the properties? And let's just think about this for a second. If I threw this marker to you, what part would you be affected by? What part of this marker would affect you?
The outside.
The outside of it. Not this unless I threw it at you, but the outside. We deal with the outside, we touch the outside, because it's the outside. Not what we do on all objects. We deal with the outside. Where are the electrons? On the outside. When you have a chemical reaction, what part changes? The outside. Are you with me? So when a chemical change happens, those electrons might change, move out here to another, right? We'll talk about that. Do we understand the attributes here? Why they determine those things? Okay, that's good to know. All right, I know I drew this kind of long, but that's it. That's the table. We good? Okay, so before we get into isotopes, let's start with what part of the table determines the number of protons?
The atomic number.
We call that the atomic number, the number of the element or the atomic number. Does that make sense, guys? Atomic number, the number of the atom, or the element number. And that's how the periodic table is organized from least to greatest atomic number. And we figured that out. Dmitri Mendeleev, he figured that out, and that's where we come up with our periodic table we have today. First, he put it in order of mass, and it was pretty close, but wasn't perfect. Okay? Are we good with the atomic number? Another number that we want to deal with is the mass number. The mass number is equal to number of protons plus number of neutrons. Does that make sense in your mind? Because the only part of the atom that has mass are the protons and neutrons. Relative mass anyway, right? We neglect the mass of an electron. Okay? So we add the number of protons and neutrons, and that's the mass. Kind of like I showed you on this periodic table. Now this number is not the mass number. We call that the atomic mass. We'll talk about the differences in just a second, or just a minute, okay? This is an average of all the different isotopes, but we'll get there, okay? Does that make sense? Okay. And let's talk about isotopes now. You guys know of any isotopes? You don't have to. I just was wondering. Okay. You ever see Spider-Man 2 with I think it's Tobey Maguire. See the second, or the better Batman's, not Batman. Did I say Batman? Spider-Man series. Okay. Well, that's just an opinion. Sorry. Okay. But he ran into Doc Ock, right? And Doc Ock, what did he do? Oh, we're not nerds. Quit it. Okay, I'm sorry. He got some tritium from Oscorp, right? And then he wanted more of it, and they wasn't going to give it to him, so he's going to steal it. Well, how did he do it? He got these long arms, right? And hooked it up to him. Anyway, not going to talk about that. But what's tritium? Tritium is an isotope of hydrogen. So let's talk about isotopes for a minute. Oh, dang. My pencil is dead again. So So let me just say, okay. So tritium is an isotope of hydrogen. So how many protons does it have? One proton, because it's hydrogen, right? Do you have to memorize that number? No, just look at the periodic table, right? Find hydrogen, say, okay, its atomic number is 1, so it has 1 proton. Good? And we should probably practice some of this before we get carried away. I'm getting carried away. Maybe we should do that while this charges. Okay? Uh-oh. Did anybody get a single-sided page? Are they all single-sided?
Yeah.
Oh, nuts. Oh my gosh, I'm making all kinds of problems today. All right. Yeah, you should have 2 of them, guys. Oh my gosh, how embarrassing. So let's look at the side that has part 1 through 5 on it. And on section 1, it just says, what's the correct atomic symbol for the following elements? That's using a periodic table and finding it and doing that, right? So rather than going through that today, you guys should become familiar with all those elements. So I'm going to skip that section. Are we good? So become familiar with those. And just know the element name and the symbol and about where it's located. Might be useful for you, okay? Don't need to know the properties, don't need to know the atomic numbers, but, okay, over time of using them, you'll get them down a little bit stronger, yeah? Okay, molecular formula. We kind of talked about this a little bit, so let's try section 2. If we have one sodium atom and one chlorine atom, what's the chemical formula? NaCl. We just wrote this one, right? Sodium is Na, so you find sodium on the periodic table, so it's Na, and there's one of them. So we don't write the one, we just write Na, right? Forgot to put record again. You guys are always, I send you the video. You guys got that video link? Okay. Sorry, it was the other class, but same, hopefully, somewhat. All right. Or did I? Oh, it's recording. Perfect. What about 2 carbon atoms and 2 hydrogen atoms? What's the chemical formula? C2H2. Pretty straightforward. Okay, let's move on to section 3. Give the numbers of each of the different atoms represented in given the molecular formula. So Li3PO4. How many lithium atoms do we have? 3. How many phosphorus atoms do we have? 1. An oxygen? 4. Are we good with that? Should we do more? What about Na4 parenthesis 2S? That's a little icky, right? How many nitrogen atoms do we have there? 2. Because there's not a number right next to nitrogen, so that's one of them, right? In the parenthesis, that 2 goes to everything inside the parenthesis. So there's 2 of those. And let me write it down. So we have NH4 parenthesis 2S. So this is saying we have 2 NH4s. Does that make sense? So if we write 2 NH4s, well, we have 2 nitrogens and how many hydrogens? 8. But an easier way is just 2 times 1, 2 times 4. You with me? And how many sulfur? We have 1. Does that make sense to everybody? Do we need other examples of that? All right, next, section 4. We can't do yet because I didn't show you. So let's continue. So isotopes. We have a symbol for isotopes, and you need to know what each thing represents. So we have, X with the A up here and a Z right here and a C right there. Why did they use these? No idea, but this is what we use. You can call them any letters you want, but this is what you'll see in the books. This is what you'll see everywhere else on the test, anything. Good? I'm not going to say what does A represent, but you need to know the top number on the left represents the mass number. And what is how do you find the mass number? Number of protons plus the number of neutrons. Good? This bottom number, that the Z, represents the atomic number, which tells us what? Yeah, number of protons. Good? And the C stands for charge. So how do you figure that out? Is it the number of electrons? It's not. Okay? So let's do some examples here. But that's what C represents, is the charge. That is determined by the number of protons and the number of electrons. Okay? Primarily the number of electrons, because that's the part that's changed. Okay? So let's see. Let's do an example. Let's do tritium now. So let's do different isotopes of hydrogen. So most hydrogen is hydrogen 1. Has 1 proton. How many neutrons? 0, right? The mass number is 1, so this is the mass number, right? Has a mass number of 1, which means protons plus neutrons. If there's 1 neutron, that means it has to be 0. Sorry, if there's 1 proton, there are 0 neutrons. You with me? Okay? And what's the charge?
Positive.
Oh, it's neutral. Why? Because there's no number there. Well, you said if there's no number, it's a 1. Not the charge. Sorry. Can we get that? Okay. So if there's a charge, there's either going to be positive something or negative something. If there's no positive or negative, then it's what? Neutral. You with me? So this is called protium. Why do we call it protium? Because basically it's a proton, yeah? Proton with an electron buzzing around it. Okay? Then we have deuterium, which is hydrogen 2. Means it has 1 proton and how many neutrons? 1, because 1 proton plus 1 neutron equals a mass number of 2. You with me? Okay. It's called deuterium. Deuterium. I think that's how you spell it. And tritium, what they use on Spider-Man to create the sun, right? Has 1 proton and...
Can you explain deuterium one more time, please?
Yeah, deuterium. So if you remember, this top number represents the mass number, which is protons plus neutrons, right? So let's write that. So 2 is equal to the number of protons plus the number of neutrons. Well, how many protons does it have? That's the bottom number that tells us the number of protons. So that's a 1. So 2 is equal to 1 plus the number of neutrons. We subtract 1 to both sides, and we got 1 is equal to the number of neutrons. That's the way to do it mathematically. Was that okay? Did you like that better or no? No, yuck. Don't ever do math again in my life. Okay, sorry. But so you don't have to do that way. You just think about it, but that's what it is. Okay? Same thing with tritium. We have 1 proton, and the mass number is 3. So 3 minus 1 is 2 neutrons. So if you just subtract these, that's going to give you the number of neutrons. Do you like that method better?
Yeah.
Yeah, the top number minus the bottom number, that's the number of neutrons. And how are you going to know? How are you going to get this down? Do it and do it and do it and do it. You feel like you got it, do it a little bit more, all right? Okay. So there's a lot of different isotopes. There's like 118 different elements and thousands of different isotopes. Thousands of them. Okay? So let's do an example to help us to understand how many protons, neutrons, and electrons are in a given isotope. Yeah? So let's say we have magnesium 25 with the 2+ charge. Any ideas how many protons there are? missing something? Do we need to know that number? Yeah, that's the number, that's the atomic number, right? For what? Magnesium. So let's go to the periodic table. Oh, here's magnesium. What's the atomic number? Oh, if it's magnesium, it's always 12. It always has 12 protons. So sometimes I won't give you that, and you'll have to look at the periodic table to determine that, right? Sometimes I will give it to you. So that's really a 12. So there's 12 protons. How many neutrons do we have? Who can tell me how to figure this out?
Do, sorry, 25 minus 12.
25 minus 12, top number minus the bottom number. And that gives what? 13. Are you with me? You will be asked questions on the test, on homework, about this, right? Okay, what about the number of electrons? How many electrons does this have? We didn't talk about it. You say 1? Why? Its charge is neutral, so all the negatives have to add up to all the positives, right? If it's neutral, you have the same number. We have 1 positive because 1 proton. You with me? Because protons are positive. Protons are positive, so that's 1 plus. And if it's neutral, you have to have 1 minus. And what's negative charged? Electrons are negative. Right, if you look at this table right up here, we have to know this. We have to know this whole table. Get it down. Good? Okay, so our charge is positive 2. Does that mean we have more protons or more electrons? More protons because our charge is positive, right? But do we know how many protons we have? Yeah. How many more protons does it have? Any guesses? 2. Because it's 2 plus. You with me? So it has 2 more protons than electrons. If it has 12 protons, how many electrons does it have? 10. Anybody want a math way to do it? Okay, here we go. We know we have 12 protons, so our charge is positive 2, and that's equal to a number of protons, or not just the number of protons, but the charge of all the protons plus the charge of all the electrons. So what's the charge of 12 protons? Positive 12. Are you with me? The charge of 1 proton is plus 1. If you have 12 of them, it's plus 12. If you have 90 of them, it's plus 90. And so on, right? Plus, we'll just say x, because we can call it e if you want. But this is what we're looking for, right? So how do we solve for x? We subtract 12 to both sides. What's a positive 2 minus 12? Negative 10, right? So if the charge of all the electrons is negative 10, how many are there? 10, because each one is negative 1. The charge of 1 electron is negative 1. If you have a charge of negative 10, then that means you must have 10 of them. Question?
Yeah, how does it turn positive?
How does this turn positive?
No, your number of electrons.
Okay. So this represents the charge of the electrons. Good question. This represents the charge of the electrons. So if you add up all electrons, you get a charge of negative 10. Well, the charge of 1 electron is negative 1. Charge of 2 electrons is negative 2. So how many electrons do you have if the total charge is negative 10? We have 10 of them. Does that make sense?
Yeah.
We good? Let's see, is there another way to think about this?
So if the charge were negative, then there would be that many more.
Yeah, should we try one?
Sure.
Well, let's do it. Any questions on how to do that? Okay? Okay, so let's see. We have, let's say, sulfur 35, let's say. And I'll just give you this number this time. We have 16, atomic number 16, 2 minus. Okay, so here we go. Number of protons, number of neutrons, number of electrons. See if you can do this on your own. If you can, keep going. If not, we'll do it together, don't worry. How many protons does this isotope have? Anybody, everybody, somebody.
45.
How many protons?
Oh, 16.
16. Are you with me? How many neutrons?
19.
How did you get 19, Ashley?
35 minus.
35 minus 16 is 19. Are we good? The charge is -2. So that means it has, in fact, do you guys like that method, or should I show you another one? Another one, just in case?
This one real quick.
Yes, we can. Thanks. Okay. Okay, so the charge is -2. That means you have more protons or more electrons?
More protons.
We've got more electrons because it's negative.
It's negatively charged. That means we have more electrons because electrons are negative. You with me?
Yeah.
Great. Is it okay if I answer wrong? Yeah, because then we learn for ourselves, right? Perfect. Keep answering. Who cares if we're right or wrong? Keep answering. Okay. So we got -2. We have how many more electrons do we have? 2 more. If we have 16 protons, that number doesn't change because it's sulfur. How many electrons do we have? 18. 2 more. Does that make sense? Does anybody need another method to determine how many electrons it has? Yeah. Okay, let's do it. All right, so if we have a regular atom that's neutrally charged, then how many protons do we have relative to how many electrons do we have?
If it's neutral.
Same number. If it's neutral, like for a regular atom that's not gone through any chemical process, then electrons equals the number of electrons equals the number of protons. If there's no number here, then it's the same number. You with me? Does that make sense to everybody? Okay? So that if it's that way, then the charge is 0. Right? So 0, hold on a sec. Maybe I should wait till we do, yeah, I didn't show you this part yet. Let's not do that yet, okay? So are you guys okay with this for a second?
Yeah.
Okay. All right, should we try some more? Okay, on this paper, sorry.
No, you're good.
Section 4, says how many protons, neutrons, electrons are contained in each of the following atoms or ions. Ions mean it's a charge, okay? A charged atom. Yeah.
Take the practice exam before due date.
Yeah. Yeah, you bet. Take it and then make sure you understand it and then take it again. Right? You got 2 chances, right? Yeah. Definitely. Okay, which one do you want to go through together? Or did you want to try some of these on your own? You tell me. Okay? So, iridium 193. You're going to need a periodic table of these, aren't you? And I didn't give you one. Dang. Come unprepared today. I'm sorry. So iridium, can anybody find iridium for me?
77.
77, perfect, right there. That means it has how many protons? 77. Can anybody tell me how many electrons it has?
77.
Why?
Because it has a neutral charge.
There's no charge here, no positive, no negative, so it's neutral. Same number of protons as electrons. You with me? 77. So if that number's 77 down there, how many neutrons do we have? How do we figure this out?
193.
193 subtract 77, which is 116? That's it. Are we good? What else? Maybe I'll have the periodic table up here so you can look at it.
And it doesn't have a charge, it's always for the number of.
Electrons is the same as protons. Yep. Yeah. Good. Are we good? Any questions? Should I give you the answers? Okay, for plutonium-244, we got 94 protons, 150 neutrons, and 94 electrons. Good there? Okay. Americium-241, 95 protons, 146 neutrons, and 95 electrons. Next one, arsenic, 77 with the -3 charge, 33 protons, 44 neutrons, 36 electrons. Cesium-133 with a positive charge, 55 protons, 78 neutrons, 54 electrons. We did iridium-193. Manganese-56 with a positive 2 charge, 25 protons, 31 neutrons, and 23 electrons. Questions? Good? All right. Okay, let's learn the last bit for this. We might have to just stop with that, right? Because we're running out of time. We'll see. Oops. All right, next thing we want to do is the atomic mass. And this is the number that is on the periodic table. And the definition or how we determine this is the weighted average of all isotopes for a given element. Does anybody know how to calculate the weighted average? Okay.
I think so.
So this is how your grades are calculated, yeah? Your test is worth 65% of your grade, yeah? Homework is like 15. Participation is another 15. And then your discussions is 5, yeah? Okay. So if you miss 5 discussions, it's probably not going to kill your grade. You with me? But if you miss 5 exams, you're done, right? Okay? They're weighted differently. So I can show you how to do it. And if you're interested in why we do it that way, I can show you that as well. Anybody want to know why? Okay, because if you understand why we do what we do, if you forget the how, you can figure out the how. That's my way of thinking. But a lot of times when I do this, people just, don't, that's just too much math, or whatever, okay? So maybe I'll do that at the end if you want it. Okay, so let's do an example here. So for example, let's say we take chlorine. Chlorine has 2 different isotopes. We have chlorine-35 and chlorine-37. Now what does that mean? If we write it this way, we can also see it this way. Chlorine-35, this is how we read it, or chlorine-37. How do you write it using the isotope symbol? Chlorine-35 and chlorine-37. Are we good? Is that the right number here? Let me double check. Yes, okay. So this is just a quick way to write it, yeah? And that's how you call it, chlorine-35. You with me? Okay. So let's figure this out, and the only way we can do this is if we know percentages, right? Let's say The chlorine 35 is 77.37%. And chlorine 37 is 22.63% of all the chlorine. You with me? Okay, so I'm going to show you how, and then I'll show you the why if you're interested. Sound good? We take the mass of chlorine 35, which is 35, and we multiply it by this percentage written as a decimal. Do you know how to do that? We'll just divide by 100, right? Change it, because percent is out of 100 per centum per 100. So divide it by 100, or move the decimal 2 places to left, and we got 0.7737. You with me? Then we add, our next one is 37. Multiply its relative abundance, which is 0.2263. Any questions how I did that? Yeah.
I may have missed the part, where'd you get the percentages? Or did you
That was given to us. Yeah, and I will give it to you. Okay? Great question. Any other questions? Okay, and that's it. That's it. That's the how. So if we do the math, 35 times 0.77367 and 37 times 0.22663, and then we add those numbers together, and we're going to get 35 point what? 45 something? 45 what? 26. We'll just say 3, round it to 3 decimal places, sure. And if we look on the periodic table, pretty close, right? Oh, so if I give you this on the test, we could just look at the periodic table. What do you think? You can use that to guide you, to say your number should be close to this, but we're going to change it just a little bit so that you actually do the math. Are you good? Question?
Yeah, so if we choose an answer because we round, will we get docked?
Depends on how much you round, right? So if we took this number right here and rounded it to 35 because, that's a 4, so we round down, then yeah, you're going to get it wrong. Okay? But do you see how it's closer to 35? Why is it closer to 35? Because that's the majority of it, right? So our number should be closer to 35 than 37. Quite a bit closer. And it is. What if you did 35.5? What if you rounded to 35.5? I would look at your percentage. Here you're given 2 decimal places, so round it to 2 decimal places. Good? But I am not going to be a freak when it comes to the test and say, oh, I'm going to get that person 35.6. No, I'm not going to do that, okay? Do you guys know how multiple choice answers are figured out? Common mistakes. That's how. But how do you check on this? You look at the periodic table, it should be close to that. Or you look at here, it's okay. Our number should be closer to 35 than 37, but somewhere in the middle, somewhere between them, right? Has to be there because it's an average. You guys know what an average is? It's the exact middle of two numbers, if you're doing two, right? Okay. Does anybody want more explanation than that? Because that's the how. Okay? All right. Do you want to practice this? So we got two practices right here. Two practice problems. Or would you rather save that and move on? Move on? Okay. So still do those. The answers are online. Okay. Let's talk about the periodic table. So we talked about how they're symbolized, right? Let's I wish I made you guys copies of this. Sorry. All right. There are three classes of elements. Oh, that's awful. And I won't give you these different classes on the periodic table. It's going to be blank like this, right? It's going to look just like this. So study this, get it down. But let's talk about the three classes. So we got metals, which is the majority of them. Non-metals. And you see that okay? Metalloids. And if you know where the metalloids are, that separates the metals from the non-metals. Is that pretty easy to know that? The diagonal star and a boron. Then there's two more. Three more. I'm not sure on this one. But see that right there? Do you know what that means? Where there's a bracket and it's not an average. It means it's so unstable, it's not found in nature. So chances are I'm not going to ask you about those. Good? So that's basically what it is. Those are the metalloids. And where are the metals on the periodic table? Everything to the left except for hydrogen. And I'm not sure about that one. I really don't know. Those are your metals. Most elements are metals. Good? And the nonmetals are on the other side.
is a metalloid based off the periodic table I pulled up.
Potassium right here,
Yeah.
it's a metal.
Oh, sorry, no,
guarantee.
not potassium, polonium.
Polonium,
Yo.
metalloid.
Yeah.
That's what my periodic table says, but I also saw another periodic table from a different book, and it was, okay, I don't know. So, but, yeah, there we go. Thank you. And who knows? I don't know if anybody knows for sure, because it's not found in nature, right? But again, no big deal. And actually, this is an outdated periodic table, so it actually goes down there. You with me? But again, these ones are unknown, or they're not unknown, but they're not really stable, so they're not found in nature anyway. Good? And of course, here's hydrogen, which is a nonmetal. Why is it over there? Because it's the king of exceptions. Okay, we'll talk a little bit more later. Okay? All right. So those are the different classes of elements. Are we good with classes? So a good test question says, okay, what class of element is chlorine? And you'd have to say nonmetal, right? Because there it is. Find it on there, and so on. You with me? Can you do that? So 3 classes. Now let's talk about the groups. We'll try to finish up the groups and be done for tonight. Do I need to, y'all have a picture of that? That's a good way to, because I didn't give you a periodic table to write on this. I'm sorry. So take a picture of that. In fact, let's say one more thing about this. Metals, what are different properties of metals? They're conductive to heat and electricity, right? We kind of know that. We're not going to stand by a flagpole during an electric storm, right? Okay? Or we're not going to hold on to a metal rod as we put it in the fire, right? Because it's conductive to heat and electricity. They're malleable, means you can change their shape. You can smack with a hammer, it's not going to break. You can run it into wire. You can, so those are basic properties of metals. We kind of understand metals a little bit because they're familiar, right? Maybe, okay? Non-metals, well, they're non-conductive, maybe good insulators. They're brittle. When you smack with a hammer, they'll break, like coal. Carbon, you ever hit a piece of coal? I don't know, I used to be a coal miner, so it's just like, okay. Anyway, but anyway, they're brittle. You hit them and they'll just shatter, break, okay? And what about the metalloids? They have properties somewhere in the middle. They're semiconductors. Well, they're just somewhere in the middle of, they're not great conductors and they're not great insulators, but somewhere in the middle, right? And that's how it is on the periodic table. So kind of easy to tell there, yeah? All right, let's do another, we got that picture? Okay, let me take another picture real quick. Kind of got it cut off. Whoops. Okay, we have different groups. This group right here. These are the alkali metals. And these are the most reactive metals. Most reactive metals. Then we got the alkaline earth. They're a little bit more they're a little bit reactive, but not as reactive. But okay. I think we should. What do you guys think? These guys over here, these are the noble gases. I want to talk a little bit more about this, so I might just give you the names and then talk a little bit more next time, yeah? And then these guys right here are the halogens. And then these guys right here are the transition metals. And these guys right here are the inner transition metals. And why do we group them up? Because elements in the same group or in the same column have similar chemical and physical properties. Why do they? Well, that's why we call it a periodic table. You guys know what periodic means? Something that does it over and over and over again. So the period of the Earth around the sun is a year, right? The period of the Earth around its own axis is 24 hours. So they just repeat, 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 repeat. So anything periodic, that's what it does. So, but what does it repeat in time periods here? It's not. So here's what happens. We go here, and then we go to the next period. And then we repeat the properties. Then we go to the next period. We repeat the properties and so on. Okay, does that kind of make sense? Kind of a rough introduction to the different groups. We'll talk more about them next time. And that's all the time we have. Hey, thank you so much. Have a great night and drive safe, please. Study, study, study. We got a test coming up on Tuesday. An exam, right? Oh, wait. Yeah, we will. We'll take it here. Bring your laptop or your tablet, whatever, not a phone, right? What was I going to say?
Are you providing this or are we bringing it?
I will give you a blank periodic table, yes. But also, you get one little 3x5 note card, double-sided, yeah? I hope you already have some of that ready.
Normal time?
Yep, normal time.
Okay,
Thank
thank you.
you. Take care. It's going to look just like this before I colored on it.
Oh, okay.
When I say it has the names and it has the symbols, yeah.
Will it be the updated version?
No, it'll be this one.
Okay. So the rows as they go across, they're grouped in those rows,
No, they're not grouped in those. They're grouped in the columns.
columns. Okay.
And the rows are periods. So, I mean,
Periods of
so lithium has certain properties.
right.
Beryllium has different properties. Boron, carbon, nitrogen, oxygen, they all have different properties. Then you come over here to sodium, similar properties to lithium.
Right. Because
Magnesium, similar properties to beryllium because they're in the same group.
because they have the same amount of electrons in the valence shell. So that
You got it.
Right. I'm taking biology at the same time.
Yep, that's it.
Right.
So we will talk about that more next time.
Yes. So I was just curious when you started talking about the rows when you strike through with the white, what that signified.
Mostly energy level. The amount of energy,
Oh.
it's not exactly that.
That's right.
because there's an exception we'll get into, and I don't think I'll teach you the exception, but
And the energy level is equivalent to the amount of electron shells.
Uh-huh.
Right, yeah,
yep, that's right.
thanks.
Yeah, you bet. Thanks for asking. We good, Manuel? Great.